Lesson 5.5 discusses inverse trigonometric functions and their graphs. So let's just make sure we recall what an inverse function is doing. So a function takes a value from the domain, say it's taking x, and then when we plug x into our function, we end up with a value, a corresponding value over in the range, let's say y. And so an inverse function is going to allow us to start with knowing what's over here in our range, but not knowing where it came from, and then be able to plug this value into our inverse function to figure out what our original value was from the domain. So let's just take a look at what that means in set notation. So if we've got this set A over here, and there's some point x over here, and then we've got a function f that takes x over here into set B, and we get set, say y. When we put x into f, we get y. And so what I'm saying is that y is what I get when I plug x inside of my function. Y is equal to f of x. Our inverse function is what we use when we don't know this value, but we want to know it, and we know this. And so our inverse function allows us then to start with a value over here, plug that in to the inverse function, and then we end up back over here getting the value that we had to start with. So f inverse y would give us x. Let's take this second equation here and write it out, but instead of putting y in there, I'm going to leave it open because I'm going to use substitution. Instead of putting y, I want to put f of x inside there. But now we already said when we put in y we get x, so when we put in f of x we're going to get x. So basically an inverse function will allow us to undo what the function did, and we get back, it cancels out. Inverse functions cancel out each other. So if f and f inverse are inverse functions, they cancel each other out, and we get back to what we started with when we put one inside of the other. Not all functions are going to have inverse functions. In fact, let's look at f of x is equal to x squared, and let's consider the fact that when I plug 2 into x squared, I get 4. When I plug negative 2 in there and I square negative 2, I get 4. So if I were trying to go the other way, if I was trying to start with the value over here and figure out where I started, I run into a problem. I don't know if I started with 2 or if I started with negative 2. And so if we try to consider the entire domain for f of x, which is all the real numbers, we're not going to have an inverse function for f of x equals to x squared. However, if I limit it, if I say, okay, well, let's don't even consider negative numbers. Let's let the domain for f of x equals x squared just be from 0 to infinity. On that much of this function, I would have an inverse function. I can define an inverse function for just this part of x squared, and it's going to be okay, because now when I start with 4, and now when I say, well, what if I had 4? What if I ended up with 4? Where did I start? I know I started with 2. There's no other place that I could have started from 0 to infinity that gives me 4 when I square it. And so I know where I started. So if we restrict the domain for functions that aren't going to otherwise have inverse functions, then we can often define an inverse function for it. That's going to be the situation that we run into with the sine function, because we're going to find that the sine function and all the other trig functions, since they're periodic, then there's going to be any value that we're trying to figure out, well, where did I start when I ended up with 0, say? Well, there's an infinite number of places where we could have started that we could have ended up with 0 for the answer when we plugged that value into the sine function. So we're going to have to restrict the domain on the sine function. Remember, one of the ways to tell if a function was going to have an inverse function was to check it out with the horizontal line test. And so using the horizontal line test on any trig function, it's going to fail. So over here on the sine function, though, we've already got it marked in red what's going to work, what a piece of the sine function that would allow us to have a corresponding value for every possible value that we get when we plug in the sine. Sine runs from -1 to 1, and if we start at negative pi over 2 and go to pi over 2 for our domain, we will have had a chance to see every value that we would get. So that's what we do when we're going to define the inverse sine function. We use a restricted sine function looking only from negative pi over 2 to pi over 2, inclusive on both ends, and we can then define y is equal to the inverse sine of x to run from -1 to 1, just like it should, and then that means that now our range for the inverse sine is going to go from negative pi over 2 to pi over 2 inclusive. And so this allows us to define an inverse function. Now, one thing that's important to remember, f inverse does not mean, this is not the exponent -1. That's not what this is to be interpreted as. So in other words, f inverse is not 1 over the function. It's a different thing altogether. It's the function that helps us go the other direction. So all of the trig functions are periodic. All of them are going to need to have a restricted domain and are going to give us a restricted range. And so there's a chart at the bottom of page 1 which will indicate what each of them has. Now, just another little detail here. Our symbol looks like this, inverse sine of x, and it's also known as arcsin. So that's another way that you might hear it referred to. But here's the table that'll give you all of the inverse trig functions, domains, and ranges.